And here's how the unique answer look like. It is parameterized by a real number beta, which is any real number between minus infinity and infinity. Okay, so this is a function that looks different as you pick different beta shape, and it's a function that acts on the vector x, okay, among say n users in the network, and turns that into a real number, into a scalar, okay, which could be positive or negative. And it turns out the following function, f parameterized by beta acting on x, will satisfy all those 5 axioms. It is the only unique family of functions that can satisfy all those axioms. And it looked like this. First of all, we're going to look at the normalized version of the x vector. So divide each xi by the summation of all the entrants in the vector. So x sub j summing from 1 to n. Okay? And we'll look at this normalized version raised to the power of 1 minus beta, then sum over all the i's from 1 up to n. Okay? And then take the 1 over beta power of this entire summation, and then put the sign of 1 minus beta in front. Okay, sign of 1 minus beta says that if 1 minus beta is positive, then this is a positive. If it's negative, then this is negative. So this function may look either very familiar or kind of strange to you. It may remind you of some kind of norm, okay? Because you are raising the normalized entrance of a vector to some power, and then take the sum and then raise to another 1 over some power. Okay, but this is to the power 1 minus beta. This is 1 over beta itself, and it may look somewhat strange to you because it doesn't kind of remind you of some of the familiar ones that you may already know. We're going to see actually it recovers many special cases we already have encountered. But first, let's take a look at this interesting example. We will compare 2 allocations. Okay, one is the allocation of 1, 2, 3, 5. Okay, this is the vector. The other is the allocation of 1, 1, 2.5, and 5. Again, for now, let's ignore the efficiency or magnitude part of the story, even though they clearly don't sum up to the same number. Just look at the distribution part among these 4 users in a network. Now, which one is more fair? It's actually not quite clear, right? This one sounds like more unfair because the gap between the largest and the second largest entry is bigger. But at the same time, the 2 smallest entries are actually identical, okay, compared to this one. So maybe this is more fair than that, or maybe this is less fair than that. I don't know. That's precisely why we need some kind of unambiguous language, such as quantification, say based on axiomatic constructions. If we plug these 2 vectors into the function f sub beta that we just talked about, then we can plot the following graph. We're plotting the numerical value of the fairness versus the parameter beta. Okay, now beta can go from minus infinity to infinity. We'll just plot the part from minus 10 to 10. As we change to different beta, we will get a different function. And we see that before beta turns to a threshold value, it turns out in this case 1, we see that this vector is deemed as more fair than this vector. Okay, slightly more fair. The fairness value are pretty close. Okay, and then past this beta, there's some discontinuity in the value, but still, this vector acts as more fair than this vector y, until a particular point. In this case, it's around 5. When beta is bigger than 5, suddenly the order changed. Okay, y vector is deemed as more fair than x vector now. Okay, although the difference is still very small. So this conforms to our intuition that says x and y are kind of hard to say which is more fair than the other. Okay, maybe X, maybe Y. And indeed, that depends on the kind of beta that you pick. Now, so what beta will we usually encounter? There are two or three views to take a look at this. One is to say, let's look at different special cases. Okay, I say beta is 1. What does this function look like in that special case? Beta is 0. Beta is minus 1. We'll do that in a minute. The second viewpoint is that, well, maybe certain kind of theory would concentrate beta in certain range, say between 0 and 1, maybe beta. It turns out that indeed is a very heavily populated range of beta in the spectrum of beta. Many different theories from sociology, statistics, computer science, and applied mathematics, operations research, you name it. They tend to develop indices where they can be recovered as special cases of our function where beta is between 0 and 1. Third, we can also try to reverse engineer this beta. Now, we've tried reverse engineering of protocols in network as well as topologies of a network. Now we try to reverse engineer beta through some human subject experiment. Okay. In fact, in one of the homework problems, we'll encounter how to reverse engineer beta by asking a sequence of binary choice questions. I'll give you two vectors, you tell me which one is more fair than the other, and then after asking you, say, 3 to 5 questions, I can tell you, hey, this actually is the underlying beta in your mind. And you may not know that yourself, but we could read your mind because that's the only short range of beta that's consistent with your preference between two vectors. Okay, so your preferences between two selected vectors through a sequence of such binary questions can give us a big hint on the beta in your mind. Now, what's the point of reverse engineering beta? Then we can say that, look, fairness is a subjective quantity no matter how we try to quantify it. Different people will have different notions of fairness in the end. But at least you should maintain the same notion of fairness whether it's talking about allocation between foes or between friends. In other words, we'll try to ask for self-consistency of notions of fairness. Okay? In other words, you can't just change your beta because you're saying, hey, I'm looking at allocation between my buddies instead of my enemies. So reverse engineering beta will allow us to say, well, now that we know your beta is, say, is 0.5, please do stick to that beta in the future as we discuss. Or you can change your mind, but then we'll say, hey, you're actually talking about a different beta now. So there are at least 3 different ways to deal with the question, what beta are we talking about? So it turns out there are quite a few interesting special cases. First, when beta goes to 1, then you can verify by L'Hopital's rule that this fairness function becomes the entropy function of x, or normalized x, because entropy supposedly acts on a probability distribution. But if you normalize the entries of x by the sum of the entries values, then you do have a distribution vector. Okay. When beta goes to 1, okay, it turns out this f sub beta of x is almost like logarithmic function. In fact, when beta is between 0 and infinity, f beta of x is almost like alpha fair utility function or isoelastic utility function that we saw so many times already, including lectures 10, 11, 14. When beta goes to minus infinity, you can verify that this function reduces to Jing's index, or the summation of entries squared over the summation of squared entries. This is basically a normalized way to look at variance of the function. Okay. And as beta goes to either positive infinity or minus infinity, then you simply get the max ratio or the mean ratio. Okay, as for example goes to minus infinity, you're basically looking at f being simply the smallest among all the n entries of the ratio. Okay, so there are a lot of special cases. There are also interesting special cases where we don't have a name for it. For example, in the range of beta from minus infinity to minus 1, actually there is no known name. So maybe we can name it after ourselves now. Now, you may have heard of something called a Gini index, which is a special case of something called majorization. That's another way to provide a partial order between vectors. Because at the heart of what we are doing in this lecture, as well as in lecture 5 and 6, and this lecture 20, is really turning vectors into scalars so that we can compare them. That is the underlying common mathematical challenge that we face in different networking contexts. So we say that two vectors, x and y, okay, have this majorization relationship. In particular, x is majorized by y. This is a curly inequality symbol between two vectors to represent that x vector is majorized by y. If, this is the definition, two things are true. One is that the summation of all the entrants in y and all the entrants in x are the same. Okay, so efficiency magnitude, again, is not part of the comparison. And furthermore, suppose I order the x and y entries in increasing order. Okay, so if they do not come in already increasing order, then I'll rearrange them. So the new vector, okay, this vector x with an arrow pointing upwards, says that this is the elements, the ith element of the x vector already sorted in ascending order. Okay. Now if I sum this from the first element, that is from the smallest element in the ascending order, up to some element d, and I look at the same thing, the assorted y vector, summing the entries from the first one to the dth one, must have the relationship that the y version is bigger than or equal to the x version for all d's. Okay, d from 1 to up to, you know, all d's n. Now when d is n, by the first condition of the definition, this inequality should be equality, of course. For example, if I look at two vectors now, 1, 2, 3, 4, okay, and another one, 1, 1, 2, 6. Now this time these two vectors do add up to the same number, which is 10. Okay, so satisfy the first condition. Now the second condition, let's see, they're already all sorted in ascending order. And this vector x and this is vector y, clearly this is satisfied for all d's from 1, 2, 3 to 4. In other words, we can say x is majorizing y. Okay, or should be the other way around. Okay, the first entrant is the same. If you add up the first two entrants, the one belonging to x is bigger than that belonging to y, and so on and so forth. Okay, so we say vector x is majorizing vector y. Now say, hey, this is a good way to do fairness comparison, except unfortunately a lot of vectors are not comparable by majorization. Neither the first nor the second vector majorize the other one, because majorization is only a partial order. Okay, still like comparing 2 points on the 2D grid. Which point is bigger? I don't know. Well, depending on which axis, x or y, you're looking at. But if I can compress this down to a single scalar for each vector, then I can always compare two scalars. Okay, because one dimension is fully ordered. And indeed, here's something called sure concave function. It has nothing to do with the concave function that we've been talking about in convex optimization. Okay, so now that convexity concavity, sure concavity says that we say a function is sure concave if acting on vector y is always less than or equal to acting on vector vector x is always less than or equal to acting on vector y for any vector x that's majorized by vector y. In other words, while two vectors have a majorization relationship, say y majorizes x, then it implies that this function must return a bigger value if the argument is y compared to when the argument is x. If a function satisfies this relationship for any xy pair that majorizes each other, then we say this function is sure concave. So many statistical dispersion or diversity indices are known to be sure concave. For example, the Gini coefficient. And it can be shown that our function f sub beta of x is also sure concave function. So that is comforting to know. Okay. But something is missing. We can actually spend another hour talking about the theorems one can prove about the properties of this function f sub beta. But let's not do that. Instead, let's just take a look at one critical issue, and that is for f sub beta of x, any beta between minus to positive infinity that you pick, different shapes of the function will always satisfy this disturbing property, that is equal allocation of resources or performance in today's lecture is still the most fair allocation. But the first thing we just said today is that equal allocation can be fair, can be most fair. Okay. There must be something missing. Okay. And there are two ways to mitigate this. One is to add different weights to different users. Okay. Let's say there are n users. Each one can have a different weight, a positive number, Q1, Q2, up to Qn. So instead of just acting on the vector x, you also act on a vector q. And indeed, one can do that. And we'll mention that a little bit in the advanced material. The second way to deal with this is efficiency, and that's the path we will pursue in the next module. Okay, we're going to say not only this this function depends on beta, it depends on another parameter called lambda that will trade off the relative importance of efficiency or magnitude for everyone versus the distribution among the competing users. Okay, so this is the path that we will take. And the way we lead into this is to look at an example of alpha fair utility function. Now we mentioned that this f sub beta of x is almost like the alpha fair utility function, u sub alpha of x. Okay, if we just let beta be alpha and live in the range of 0 to positive infinity, forget about the range where it is negative. Okay, alpha fair is not defined for that range of alpha, so we just skip that part for now. But for this part, if we just let beta be alpha, is our function the same as isoelastic utility or alpha fair utility? Not quite, almost. And we will see what exactly that is and how that helps us to understand the trade-off between efficiency and fairness in the next module.